Hello! I'm Professor Von Schmohawk, and welcome to YU. In the last lecture, we saw how a system of three linear equations and three variables could be used to solve a problem with three unknown quantities: the price of a ticket, the price of a drink, and the price of popcorn. We knew that three different groups of people had purchased different quantities of these items, and the total price that each group paid. Given this information, we were able to create three mathematical relationships involving these unknowns. We then solved this system of three linear equations and three variables to determine the price of a ticket, the price of a drink, and the price of popcorn. Together, these three values form the single unique solution to this system of equations. Now let's look at an example of how a system of three linear equations and three variables can be used to solve a real-world problem represented by an equation which is not linear. Hoping to break the YU altitude record for student slingshot launches, A.V. Geekman has constructed a giant slingshot which he plans to use to launch himself into the YU campus pond. He knows that objects in free fall always follow a parabolic path. He also knows that the standard form equation for any parabola with a vertical axis is y equals ax squared plus bx plus c, where x and y are the horizontal and vertical coordinates of the parabola, and a, b, and c are numbers which determine the dimensions and orientation of the parabola. However, since this is the first test flight of this highly technical apparatus, AV does not know exactly what his parabolic trajectory will be. To determine whether he has attained sufficient altitude to break the record, AV has set up a camera to automatically take photos of his flight. The camera captures three images of AV's flight, one on the way up, one on the way down, and one at the point that he makes contact with terra firma. Unfortunately, none of these photos recorded the point that he reached his maximum altitude. However, from these photos, AV can determine the x and y coordinates of his position at three different points during his flight. If he can somehow use this data to construct the equation for his parabolic trajectory, then he could use that equation to determine the maximum altitude attained during his flight. Since the equation for a parabola is y equals ax squared plus bx plus c, he only needs to determine the values of a, b, and c in order to construct the equation for his path. At this point, you may be thinking, but wait, the equation for a parabola is not linear. Linear equations do not have squared variables, and x is squared. However, the unknown quantities which we must calculate in this equation are a, b, and c. Therefore, in this problem, a, b, and c are the variables, which of course are not squared. Because AV has recorded the x and y coordinates of three different positions along his trajectory, we can substitute these values for x and y into the equation for a parabola, thereby creating three different linear equations and three variables a, b, and c. Now we have a system of three linear equations and three variables a, b, and c. Let's start by writing these equations in standard form. We can now solve this system to determine the values of the variables a, b, and c. We will start by eliminating the variable c using the first and third equations. Multiplying the bottom equation by -1 and adding the equations, we get negative 140a minus 10b equals 5. Or dividing by 5, negative 28a minus 2b equals 1. We will now eliminate c again, using the second and third equations. Multiplying the top equation by negative 1 and adding the equations, we get 44a plus 2b equals negative 5. This system of two equations and two variables can now be solved to find the values of a and b. Adding the equations, we get 16a equals negative 4. Or dividing by 16, a equals negative 1/4. This value can now be substituted for a in either of the two equations to find the value of b. Substituting negative 1/4 for a in the bottom equation, we get negative 11 plus 2b equals negative 5. And adding 11 to both sides, we get 2b equals 6, or b equals 3. Now that we know the values of a and b, we can substitute those values back into any of the original equations and solve for c. Choosing the top equation, we complete the arithmetic to get 5 plus c equals 6. Subtracting 5 from both sides, gives us c equals 1. Now that we have solved this system to find the values of a, b, and c, we can plug those values into the equation for a parabola to produce the specific equation for AV's parabolic trajectory. Graphing this equation, we see that the graph includes the positions of all 3 points recorded by the photos, and that AV achieved a maximum altitude of 10 meters. Setting a new altitude record for YU student slingshot launches. In a future algebra lecture, we will see that it is not necessary to physically plot the equation for a parabola in order to determine its maximum height. It is possible to convert the standard form equation for a parabola to what is called vertex form, where h and k are the coordinates of the highest or lowest point on the parabola. Even though this problem may seem quite different from the problem we solved in the previous lecture, which involved calculating the prices of 3 items, both problems were similar in that they both had 3 unknowns, in this case the values of a, b, and c, and we were able to construct 3 linear equations involving these unknowns. And once again, since there were at least as many independent equations as unknowns, it was possible to determine unique values for each unknown. Together, these 3 values form the single unique solution to this system of equations. In this last example, we saw that systems of linear equations can be used to calculate shapes which are not linear, such as the equation for a parabolic trajectory. In the next lecture, we will use a system of 3 linear equations and 3 variables to calculate a different kind of nonlinear shape.